Hello chemists, today we are going to be doing some extra stuff with electron configurations, and then we're going to move on to introducing some stuff about periodic trends. That is the way that elements change as you move through the periodic table. First off, I want us to go back to thinking about how you write the electron configuration of atoms, including subshells and orbitals. As an example, let's take titanium here. So titanium, it's right there. It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Total of 22 electrons. That's normal titanium. Titanium has an exception in the way that you make it into an ion, though. When you're making things into ions that have 4s orbitals, when you remove ions or electrons to make a positive ion, you remove them from the 4s orbital before the 3d orbital. You add electrons when you're writing out the configuration to the 4s first. You remove them from the 4s first as well, rather than removing them from the 3d first. So, with that in mind, this is titanium, but this is titanium 3+. As you can see, I've removed 3 electrons to make it a 3+ ion, and rather than removing 2 electrons from the 3d subshell and 1 electron from the 4s subshell to make it 4s1, I instead removed 2 electrons from the 4s subshell, because you remove from the 4s first, and 1 electron from the 3d subshell, thereby making it 3p6, 3d1. So there's no 4s electrons in this at all. The reason for that is because the 4s orbital, despite being a 4th shell orbital, is lower energy than the 3d orbital. Just something to keep in mind when you're making positive ions of things that go up past 4s. Doesn't affect 3s or 2s, just 4s. So this is titanium also, but it's a pain in the butt to write that whole big long thing every time. So there's a kind of a shorthand, which some of you have already discovered. This shorthand looks like this. You go to the periodic table, you look for what the noble gas that is closest to it and of a smaller atomic mass, so in this case it's argon, and you can write in brackets argon like that. And what you're doing when you do that is you're saying the electron configuration argon plus 4s2 3d2. If we look up here, the electron configuration of argon is this. So the 1s2 through the 3p6, that's argon. What we're doing down here is we're saying argon plus a few bits. It's just a way to save some time. You don't have to do it, but you can if you're interested in saving just a little bit of time. Also, there are some exceptions to the way we fill subshells. Chromium and copper are both exceptions. Chromium and copper don't fill up in the same order as anything else because a half-full shell, subshell, is almost as stable as a full subshell. So rather than totally filling a subshell and then partially filling the next, you will half fill 2 adjacent subshells. There'll be a question about that in the questions to this video. I want you to go find out more about those exceptions yourselves. Okay, so that's the last bit about electron configuration. You'll need to keep that in mind though when we talk about periodic trends. So periodic trends are basically why the periodic table is arranged the way that it is. If we, oh, sorry, I forgot I put this picture in here. This is a picture of a knife that some guy made out of bismuth. That's it. I thought it was neat. Moving on. So here we look at the periodic table. As I pointed out to you guys before, this is actually arranged in kind of orbital order. We've got our 1s1, our 1s2, our 2s1, our 2s2, our 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, and on throughout the periodic table. So it's arranged in a way that makes sense with electron configurations. It's also arranged in a way that matches the atomic radius. So if you go down the periodic table, that is this direction, your atomic radius gets bigger. That makes a lot of sense. As we go down the periodic table, our atoms are getting bigger. They have more electrons, so we would expect the atomic radius to get bigger. The atomic radius is just if you measure from one side of the atom to the other, imagine taking an atom and stretching a very, very small measuring tape across it. That's the atomic radius, how far across it is. So as we go down the periodic table, like this, our atoms get bigger. That makes sense. But as we go to the right across the periodic table, atoms don't get bigger, they get smaller. You would expect, since Titanium has got more electrons than scandium. You'd expect it to have a bigger atomic radius, but in fact it doesn't. It has a smaller one. Ytterbium, right down here, has a much bigger atomic radius than scandium, but titanium has a smaller one. The reason for that has to do with protons, and it has to do with shells. As we move across the periodic table here, we are staying in the same shell. We're in the 1, 2, 3, 4th shell, because we're in period 4. So all of those electrons are being added to the same shell. That is, they're being added at roughly the same energy distance from the nucleus. However, every time we move one up the periodic table from scandium to titanium, from titanium to vanadium, from vanadium to chromium, we're adding one proton. And those protons have a positive charge. As we add a positive charge to the nucleus, it exerts a greater attraction on the atoms that are in the outside of the in the shells around it. So basically, you're making the nucleus more positive, but you're not giving the electrons any more energy to get away from them because they're being added to the same shell. That means that the nucleus exerts a stronger pull on the electrons that are in the shell, and it pulls the shell closer to the nucleus. You get a smaller atomic radius because more protons exerting an energy on the same kind of level of electrons pulls them all in closer. As you go down the periodic table, the reason you don't get that effect still happening is because for instance, from 4 to 5, you're moving up an energy level. You're moving up a shell. And that movement up a shell means that there's now a shell between you and the nucleus, between the valence electrons and the nucleus. So as we go from here to here, and we add the shell, we're actually adding a layer of electrons in between the valence electrons and the nucleus, and that shields them. So you have a shielding effect coming in as you go down the periodic table that doesn't come in as you go across the periodic table to the right. All right, so that is at atomic radius. Ionic radius is very similar, and I'm aware I'm running short of time, so I'll try to keep this quick. The rules for atomic radius are also true for ionic radius, but with ionic radius you have to keep track of where the electrons you're adding or removing are coming from and going to. So if we start, for instance, with chlorine, and we add an electron to it to make a Cl- ion, that ion is going to be bigger than the atom because we've added an electron to it. And ditto with the other way around. If we removed an ion from it, the atomic radius would be smaller. That's it.